Hello everyone. In this part of the lectures on the frequency domain analysis of the systems, of the closed loop systems, we will focus on the Nyquist criterion and stability margins. So initially we will start with an argument, the principle which is called as the argument principle, and then we will switch to the Nyquist criterion, and we will see how the stability of the closed loop system could be determined by using the Nyquist diagram. Alright, so let's get back to the argument principle. So basically, for the argument principle, we need to consider a transfer function at first, something like h1, where we have a set of zeros and poles. So for this example, we have two poles and two zeros. All of them are on the left half plane. The zeros are in the form of a complex conjugate, and we have two real poles on the real axis. Then we have also a clockwise contour. We call it C1. And the contour is here. Basically, it is a closed path, starting from a point and then moving in the clockwise way and then getting back to the same point. Now, we want to evaluate the values of h indeed. So we want to evaluate h1 of s on the contour. This will give us a map of h1 indeed. So if we do that for any given point on the contour, like S0, S1, S2, S3, S4, and so on and so forth, for the points on the contour, for the evaluation of h1 at that point, we will get a complex value, which could be divided into the amplitude and into the angle or phase. Alpha here is called as the argument or angle of h1 of S0, and it could be obtained as θ1 plus θ2 minus phi1 minus phi2. Let's see what are θ's and phi's over here. If you check the poles and zeros that we have for this system, let me clean the area and then show you the angles first. We have two poles here and two zeros. In order to evaluate the angle contribution from the zeros and from the poles at a given point like S0 that we have here, we need to connect that zero or pole to the point S0, draw a straight line in parallel with the real axis towards plus infinity from that zero or pole, and then find the angle between that line, the horizontal line, and the line which connects the zero and the pole to the point like S0. Okay, my laptop responses with a delay to my actions. Sorry for that, but nevertheless, you can see the angles over here. So we have two zeros. For the first zero, which is here, we connect it to the point S0. We have a straight line towards plus infinity, and the angle here is θ1. Similarly, for the second zero here, we have a straight line towards plus infinity in parallel with the real axis. We have the piece of line connecting that zero to the test point S0, and here we have the θ2 angle. So for the zeros, we have θ1, θ2, and similarly for the poles, we have phi1, which is this angle, and phi2, which is this angle. I can use another color to highlight the angle that we have as phi2. So basically, alpha will be obtained as sum of theta i's minus sum of phi i's. This comes from the zeros, and this comes from the poles. As the point S0 transverses over the contour in the clockwise way, the value of alpha changes. It changes because the value for theta 1, theta 2, phi 1, and phi 2 change. As those values change, the value of alpha will also change. For this example, since there are no poles and zeros inside C1, the amount of the change that happens for alpha will not go beyond 360 degrees indeed. So it will not reach 360 degrees, the net change that we have for the alpha. And as a result, the plot of H1, as you can see over here, will not encircle the origin, because the net amount of the change that we have for the alpha is below or is smaller than 360 degrees. So I can maybe give you some points. This is the starting point. If we say that we start on the real axis, as we move on the contour in the clockwise way, the movement will be in this way indeed. We'll arrive at this point, and then by moving on the contour again towards the starting point, we will end up with this map. At each point there will be the amplitude, which depends on where we are on the contour, and the given angle. But you can see that the angle span that we have for the mapping will be between, maybe we have the maximum angle here and the minimum angle here, but you can see that, and this is indeed what we have for alpha. The alpha will be, for this example, will be, let's say, between minus pi over 4 and plus pi over 4, for example. Yeah, the exact values might be a little bit different than what I have written here, but we can see that the net amount of the change is smaller than 360 degrees. It's indeed alpha changes for pi over to the overall range of the change, and as a result the mapping will not encircle the origin. And as we'll see later, this is because there are no poles or zeros inside C1. Now we can consider the next example. Let's say we have a function as h2, the transfer function, and for our h2 transfer function, the poles and zeros are located as you can see here. So basically we have a pole inside C1. In this case, as the S0 or S transverses C1 in the clockwise direction, the contribution that we have for theta 1 and theta 2, which come from the zeros, and phi 1, which comes from the pole outside the contour, will change, but they will return to their original value as S returns to S0. On the other hand, for phi 2, which is the angle contribution that we have from the pole inside the contour, the phi 2 will undergo a net change of minus 360 degrees as the point S0 transverses over C1. And as a consequence, the value of alpha will undergo the same change. And it means that H2, the mapping of the H2, will encircle the origin in the counterclockwise direction one time. So let's see how phi 2 undergoes a net change of minus 360 degrees. So if we start on the real axis, if we set our starting point here, for phi 2 we will have the angle of 180 degrees. So we will have 180 degrees for the angle, which is basically this point. And as we move over the contour at some point like this point, if I call it S1, the angle that we have will become 90 degrees, which is indeed this point. So we'll move, the mapping of H1 will move in this direction. And then if we continue to move on the contour C1, the angle that we get will be equal to 0 degrees, and that will be this point. So as we arrive here, we will get the angle of 0, and then as we move, as we continue to move on the contour in this way, at some point the angle will become minus 90 degrees, which is this point, that corresponds to that point, and it will become smaller and smaller until it reaches this point where we have the angle of minus 180, and we will be at this point. So we started at plus 180 and we ended up at minus 180, and as a result the net amount of change that we have for the phi 2 angle is equal to minus 360 degrees. If instead of a pole inside the contour we had a 0, then H2 would have encircled the origin in the clockwise direction. Okay, so this is something important to keep in mind. Here we have the argument principle. A contour map of a complex function like H1 or H2 will encircle the origin clockwise z minus p times, where z is the number of the zeros and p is the number of the poles of the function, of the transfer function inside the contour. So for the example that we had here, we have no zeros inside the contour, so z is equal to 0. We have one pole inside the contour. As a result, z minus p is equal to 0 minus 1. So we have minus 1 clockwise encirclements, and this is equivalent to a counterclockwise encirclement, and we see that it is the case. Okay, so basically what I was explaining to you in terms of the changes that we had for phi 2, it was from minus 180 to from plus 180 to minus 180. But in terms of the mapping of H2 here, we have the counterclockwise movement. So if you go back, you should double check this, okay? What I explained here was for phi 2, but I explained it over the contour map of H2. But nevertheless, the concept is still there. For the first example that we had here, we have z equal to 0, p is equal to 0. As a result, z minus p is equal to 0, and we have no encirclements. And you can see that we have no encirclements around the origin over here as well. Alright, so that's basically the argument principle, and we will use this in order to form our Nyquist criterion for the stability of the closed loop system. Before starting that, we will indeed consider the contour C1, as you can see over here, in order to find the mapping of the H. The C1 contour will cover indeed the whole right hand plane. The whole right hand plane will be inside our contour. The contour will have this segment where we have s equal to j omega with omega between 0 and plus infinity. We have s equal to j omega for omega between minus infinity and 0. And we have this semicircle over here with the angle which approaches plus infinity in order to cover the whole right half plane. Then if you want to discuss about encirclement of the origin, we will consider the pose and zeros of H inside this contour, which means that the pose or zeros in the right half plane. And then we will see how to use this in order to discuss the stability of the closed loop systems. Alright, so I think that's all for this video. Thank you for watching. In the next video, we will discuss more about the Nyquist stability criteria. See you in the next video. Bye for now.